Good day, everyone. Thanks for joining us today for our webinar on transmission and distribution system planning basics. My name is Pete Kappers. I'm from Lawrence Berkeley National Laboratory, and my colleagues, Jose Lara and Vince Westfallen from the National Renewable Energy Laboratory will be presenting on this topic to you today. This is actually part of a broader webinar series that we are holding and recording. If you could jump to the next slide. And it's being funded by the Department of Energy. Very important to, give a shout out to the wonderful folks there who were able to make this and the rest of the webinars in this series possible. If you could jump to the next slide, I can give you a little bit more insight into that series. We started out our very first one giving a high-level overview of it and the connections associated with forecasting and resource adequacy to broader state planning efforts. We then moved into a series of topics focusing specifically on forecasting, first providing a general overview of methods and techniques and tools, then moving into specific topics associated with load expansion and distributed energy resources. Then we moved into the topic of resource adequacy. And so our first webinar there on the next slide, you can see it was associated with just providing some of the basics, again, methods, tools, and techniques. And then we're coming to today's topic where we're focusing on transmission and distribution system planning. Again, some of the basics associated with it, tools, techniques, and methodologies. And then we end up our webinar series talking about the evolution of resource accreditation. So with that, I want to hand things over and get us started to Jose Lara from the National Renewable Energy Laboratory. Take it away, Jose.
Thank you, Peter. Yeah, so in this part of the conversation, we're going to talk about transmission planning. And transmission planning, we'll discuss why is it important and what kind of modeling matters when we're doing transmission planning, and which are the challenges that exist by incorporating new technologies in these transmission planning and assessments, and how we can address it. So let's go. The basics of transmission planning is that it has evolved dramatically from the situation where in the first part of the 20th century up to kind of the 80s, it was done unilaterally sort of by utilities. Utilities will define the infrastructure and then just get a rate base of that infrastructure. In today's market restructure systems, we have a set of processes that make sure that the transmission investment and transmission planning happens within a particular set of rules, such that the ratepayers can actually reap the benefits of those investments in the most effective way. And transmission planning is based on three classes of investments. The first one is reliability projects, which are projects that need to happen and are projects that are determined when NERC standards for reliability couldn't be met. Then we have economic projects, which are the ones that we see in the news often and the kind of that are subject to a lot of different discussions that are meant to reduce congestion, lower production cost, and require a rigorous cost-benefit analysis. And we're going to go into the details in this presentation about what does it take to do this cost-benefit analysis and why is it so difficult. And finally, we have public policy projects, which are projects that are required to enable state mandates or integrate generation and meet certain targets that states have according to their policies. So if we take this framework, we can now start understanding what kind of modeling and what kind of simulation is required in every different case to be able to answer the question of how do I assess my transmission planning effort. Let's go to the next slide. So the other part that is important we're going to be talking about in this presentation is this new terminology that shows up a lot, which is called GETS, and understanding how GETS get incorporated in the transmission planning. And we're going to look at the process of in understanding that these technologies are operational. They change how the system operates and how do we actually incorporate them as a way of evaluating cost and benefits. Also, we have to understand that GETS, depending on how they're deployed and in conjunction with a broader portfolio, they can actually increase reliability and include cost benefits. So let's go to the next slide. Right, so these type of technologies are more difficult to assess because they're meant to be operating kind of like more in the two other categories that are not reliability. They're economic projects and they're public policy projects. So the impact of GETS is more dynamic. It changes, depends on the system conditions, and it changes depends on the requirements that we have at a particular location of the grid. So modeling gets more difficult when we have to start including this level of operational detail and understanding how just a couple of snapshots that are reliability based, as they're usually done by the utilities, might not be able to capture their full value. And we're going to discuss different techniques that we can implement to allow us to capture the value of gets in different contexts. You go to the next slide. So the first part that we discuss is this reliability-based planning. Reliability-based planning is very regulated. It's very clear what the requirements are, and it's regulated under the NERC TPL 001 5.1. The transmission reliability criteria, basically what it says is that this is the table that we have in the screen. I'm not going to read it all, but this standard basically says what needs to happen when the system sees a fault and sees some component going offline. And the requirement says that you have to be able to maintain regular operations, even if you lose one component in the system, that you have to avoid cascading events and situations of that kind. And it also explains that the type of requirements under extreme cold and extreme events conditions. So every kind of project that wants to be built, because this standard is not being met, has a different track and a different speed at which can be implemented. Normally, this process is kind of like more focused on the engineering side and understanding the reliability of the system. And it tends to require less analysis from the perspective of a cost benefit, like the other ones that we've seen in the list of planning criteria. Let's go to the next slide. Right, so throughout the process, we're going to discuss what is the current state of practice, what is the ideal case, like the two extremes of like what would be the ideal way to incorporate transmission planning and the state of practice, and then figure out what is a middle ground of improved modeling that includes enough fidelity to have good decision making, but at the same time is something that we can realistically solve within our organizations. Continue the next slide. So the terminology we're going to choose for this analysis is, on the one hand, we're going to have a technology portfolio. There's a collection of projects designed to address a grid need. This can include multiple new lines, can include reconductoring, and can include gets, right? Can include different set of additions to the grid that we want to include, can also include some kind of other type of components like static bar compensators or capacitors. And then there's the set of scenarios, which are the assumptions under which we want to assess the value and performance of this portfolio. So for example, we want to understand if the portfolio that we're choosing is capable of sustaining through different degrees of renewable energy integration. We want to understand if this new portfolio will help with integration of new load, or can it actually make us go through some kind of winter storm or some fire events in different areas, right? So we're going to think about this of like every portfolio has to be assessed across the same number of scenarios. So let's go to the next slide. And in the ideal case for transmission planning, like if we had this capacity that doesn't really exist at large scale, we will actually plug in all these future scenarios and all of these technology portfolios, and there will be some singular model that is able to make the decision for us about what is the optimal technology portfolio and deployment schedule. So this problem, right, is incredibly computationally challenging. It's very intractable when you start having to take into account details about AC representation. It actually starts requiring many more samples of time periods in order to capture the value of gets. And, this is kind of something that is more like a research base. So like, if we have this idea about this ideal situation where we can plug all of this information and work backwards from it, we can understand the current practice and improve modeling alternatives. So let's continue going forward. So the existing state of practice, the other end of the spectrum, is that we put these technology portfolios and future scenarios into what is called a production cost modeling. And that gives us some idea about the costs and benefits from the economics perspective and the cost perspective of these portfolios in conjunction with other assumptions about what is my fleet, what is my increasing load, and so on. And in a separate track, then some of these portfolios and some predefined snapshots and scenarios get put into power flow analysis where reliability analysis is conducted. And the only answer we get out of it is whether the solution meets the reliability constraints. So whether the production cost modeling is almost regularly conducted by PUCs or energy offices or state agencies, the reliability analysis has historically been left to the operators and the utilities to conduct. So we have two questions that we have to answer in conjunction about what are the reliability impacts of a particular portfolio, but we also need to answer what are the economics. And historically, this is done in a disjointed fashion, right? So these processes that happen separately are the exact opposite from the last slide that does all of them together. So let's go to the next slide. Now, the shortcomings of this, again, is that a lot of these IRP models and all of the economic models are actually not even a full representation of the transmission grid. So when it comes to transmission planning, the planners actually run zonal models, they calculate the IRPs, they do these kind of processes of understanding what the generation fleet looks like. And the nodal models sometimes don't actually reflect the details that went into those models, and the IRP doesn't reflect the reliability constraints and reliability concerns that can come from the utilities. So this limited ability to capture the value of both of the modelings within the same framework creates a lot of the challenges that we observe, where there's a lot of back and forth between the utility or between the ISO and the local states and different regulators to try to converge to a collection of scenarios and portfolios that make sense for both type of modeling approaches. So let's go to the next slide. So, for example, here you can see this is on the bottom left. This is the only scenarios that get usually tested and predefined for the power flow analysis. So if I have an IRP where I needed to conduct a yearly analysis to calculate cost and benefits, then I have to evaluate its reliability only using very specific set of cases that are predefined, completely disjointed from the PCM or the production cost analysis conducted. So these predefined snapshots have a reliability-based case and have assumptions that don't match the actual operational regimes observed from the previous modeling. And the reality is that even though these analyses are done to conduct the investments that we want to do for reliability improvements, they actually don't provide any guarantees that those reliability improvements will be met, given that there is no input from operational conditions obtained from the previous simulation. Continue to the next slide. So what happens is that then you have, again, this iterative planning process with power flow, where some capacity expansion happens, some analysis gets disaggregated. That disaggregation process in itself sometimes is not fully transparent or not fully clear about how it happens, requires a lot of manual input. Then you conduct your transmission expansion analysis, conduct your power flow, and if it's not sufficient, goes back into the expansion, and then you have to aggregate again to put it into your expansion program, disaggregate it again. And this cycle of models that can actually take long time, right? So this is what we observe, big cycles of planning processes in the industry that can take multiple years. Let's go to the next slide. Right, and there is challenges like including the power flow and checking that the convergence of the power flow works for multiple PCM results is not easy. We have these large residuals that can end up from our Newton-Raphson. Our tools are not necessarily meant to be able to address potential differences between the outputs coming from the planning scheduling and the actual physical AC power flow that we want to resolve. So developing the capabilities that are needed to be able to solve these things inside of one with each other is one of the bigger improvements that we can have when we want to evaluate these things. We can actually go and say, how can I take my power flow risk, my PCM set points, the operational snapshots that I obtain from more realistic operation conditions, and put it into my power flow. So this is one of the challenges that is pending that the National Lab will work at trying to resolve and try to deploy in industry to improve the current state of practice. And a lot of the work that we do under this TA program. Let's go to the next slide. Right, so what we understand is like we can have this iterative process, and this is kind of like an improved state of practice where you have an unconstrained PCM that then runs into a DC power flow. We obtain new constraints from the power flow, incorporate them into the production cost modeling, run contingencies, obtain new constraints, and slowly but surely, the addition of new constraints from informed by the power flow allows us to implement those in the PCM to tighten up better our cost assumptions. So this transition between the different operating conditions is basically very challenging, but it's a much better process than having fully disjointed approaches, because we can make sure that the costs that we're observing in our PCM actually reflect the system transmission constraints as they happen in practice, right? So the more refinement you do and the more inclusion of the reliability aspects into your modeling, the more also costly becomes to run this analysis and the more simulation time that you need. And because you're going from simple unconstrained systems to have more constrained systems as you move forward. And this is the processes that, for example, were conducted for the National Transmission Planning Project. Let's continue with the next slide. Right, so this is where the improved modeling and this reliability-aware production cost comes to play. So what we do is that we actually run a production cost modeling that instead of evaluating the contingencies outside, we actually integrate the contingencies inside of the model. So we get the technology portfolios, the feature scenarios, and these different scenarios get evaluated in the reliability-aware production cost. Once we actually get the reliability-aware production cost, we actually get a much better picture about what are the restrictions that will be observed in the dispatch of our units given those reliability constraints. We then can actually also go back into power flow analysis and understand if there's AC power flow challenges with it. And given that we obtained already reliability constraint outputs from the reliability aware production cost modeling, the likelihood we get a proper power flow result gets higher, right? So even though there's, this is what we call power flow in the loop, and it's able to capture these reliability impacts across a wider range of operational conditions. So it becomes easier to build consensus across the state agencies and the utilities because this common framework answers both questions. What are my cost benefits, including reliability constraints, and also kind of have some sense of whether those reliability constraints actually will keep the system safe once I conduct the power flow analysis. So let's go to the next slide. Of course, this process can be more computationally costly, but in many cases, a lot of these analyses are conducted within regions. For example, different states will want to assess their own state conditions. So Virginia might need to know what the transmission requirements are for its local region, which doesn't mean that we need to model all the way up the PGM grid that extends to Illinois. So what we do is that we can tackle the challenge of the computational increase in the demanding increase by having a reduction of the system. So we can take equivalents around our study region and simplify those areas around the study region such that we can then reduce the size of the problem without necessarily losing the key components that we need to understand transmission impacts within our areas. So we basically conduct this process of aggregation where we take the areas of the network that don't impact greatly the local study region, and we can then include the security constraints within the study region pieces, right? So in this particular way, we can still create this capacity to have consensus between the utilities and the state agencies and tackle some of these challenges with the security constraint models that can be computationally costly to solve. Let's go to the next slide. Right, and then finally, what we can do is that we can also figure out which internal parts of the study region are critical for security constraint or not by pre-calculating radial networks. We can reduce degree 2 nodes that are not needed. So we can do a lot of pre-processing of these models that don't change the results, but they allow us to actually have a less complicated method to manage the computational difficulties, right? So the whole procedure goes from these big systems to smaller ones that still answer questions about the specific lines and projects and portfolios, and we can actually obtain results that even in the optimization side are simplified, and we can evaluate the full power flow. And the utilities and the agencies can communicate each other about the capability that the system have to operate correctly and within the reliability standards. Let's go to the next slide. Right, so in conclusion, what we've seen is that there is a need to marry these problems of economic cost benefit with reliability analysis. There's a state of practice today that's decoupled cost and reliability that creates a lot of churn and a lot of iteration and challenges of two processes that don't really talk to each other. We know that there is an ideal case where everything gets into the same bucket and these massive models can make the decisions for us all together. And in the middle, we just describe two potentially improved modeling approaches. One where the reliability constraints are integrated outside of the PCM modeling, and one where the reliability constraints can be implemented inside of the PCM modeling, such that the two considerations can be evaluated at the same time. I'm going to now pass it on to Vince to talk about distribution planning.
All right, thanks very much, Jose. I'm going to focus mainly on system planning from a distribution perspective, and I really hope to show why the shift that is happening these days from traditional siloed planning of transmission and distribution systems to an integrated approach is necessary. Would you go to the next slide, please, Raphael? So every system level is feeling the pressure from these four spending drivers: aging infrastructure, resilience, and growth. Growth from existing customers as well as new customers, and especially these days, data centers. Distribution, transmission, and generation planners are all dealing with these, and by integrating their planning, there really is potential to save billions of dollars through multi-objective investments rather than siloed decisions surrounding aging infrastructure, capacity expansion, and resilience. Bottom line is industry needs to move from siloed planning to integrated planning. Next slide, please. I want to look at four of the main challenges that are in front and center in distribution these days. Next slide, please. First, we have the blend of these two issues: aging infrastructure and weather. Facilities need to be updated, and we want those updates to enhance reliability and resilience. The chart on the right shows a year-by-year average SAIDI, that's System Average Interruption Duration Index. Now the blue at the bottom of those bars is without major event days. Light blue is with those major events, and green at the tips of the bars is loss of source. Loss of source is responsible for about 20 minutes of annual outage time. Blue and light blue are distribution outages that account for about 300 outage minutes each year. So you can see why reliability is a big concern in the distribution world. This plot on the left is from some work we did last year, looking at the state of service transformer fleets across the nation. Although it's just one category of assets, it gives a good illustration of the age of equipment that's out there. When an investment is needed for a new load, justification can be pretty straightforward. Once the load is validated, planners will lay out some alternatives of what needs to be done to serve that load, and then ultimately what was chosen and why. Now, it's more challenging to quantify relationship of investment to reliability and resilience. New sets of metrics to quantify resilience is a big topic in the industry. Bottom line here is that these decisions have to be made strategically: when, where, and how to invest to maximize improved reliability and resilience. Next slide, please. For the past 2 decades, load has plateaued, but it is expected to ramp significantly beginning in the very near future. Existing customers' loads will increase as they adopt technologies like electric vehicles, and we're seeing tremendous potential growth in segments like data centers on the bottom right there. Here's an interesting contrast in viewpoints. Distribution planners care very much about granularity, which substation and which feeders are going to see the growth, whereas transmission planners are interested in aggregates. And this leads to different timelines, time horizons that each team is used to. Distribution, the next 2 to 5 years are very important. And in transmission and generation, well, those folks are working out a decade or even longer. Forecasting is a basic activity at all system levels, but more and more, planners need to work in the other levels domains. Next slide, please. DER integration. As we work throughout the industry on DER integration topics, we find that this is another interesting topic. Interconnection, of course, happens in the distribution world, where distribution priorities are local impacts like feeder voltage, reverse power, and thermal constraints, while transmission and generation priorities are bulk system impacts like resource ride-through, and then markets such as frequency regulation, and of course the availability of these resources. Bulk system priorities need to be identified and satisfied via local control when possible during DER distribution system interconnection. Next slide, please. With potentially orders of magnitude increases in connected devices operating autonomously, and the vast majority being owned by customers, this presents a lot of hardware and software uncertainties for all of this new equipment. Cybersecurity for the evolving grid is and will continue to be critical. Next slide, please. Next, we're going to move on to some of the trends that we're seeing in the industry as utilities grapple with these challenges. Next slide, please. Integrated distribution planning. As I said earlier, integrated planning really has potential to save billions of dollars through multi-objective investments rather than siloed decisions around aging infrastructure, capacity expansion, and resilience. And this can happen by making these practices more cohesive, inclusive, and transparent. It's tough to just touch on this topic and try to do it any kind of real justice. As we've worked with utilities and regulators in the integrated planning space, I would say that integrated planning involves advancing these activities in two distinct dimensions: in depth throughout all system levels, distribution, transmission, generation, and you could probably add customer also. And then in breadth, integrating needs and objectives that are beyond what is traditionally included in planning. Next slide, please. Resilience planning incorporates new ways of looking at outage events, focusing not just on single outages, but on the entire event evolution, from the beginning of a storm all the way through to final restoration. And as I mentioned, new ways of looking at things requires new ways of measuring them. Again, it's a new challenge to planners to justify these investments and to quantify the relationship of investment to reliability and resilience benefit. We're seeing that regulators and utilities are coming up with some pretty sophisticated frameworks and methodologies to move practices along the continuum from reliability to resilience. Next slide, please. You can see we have listed out here some of the facets of forecasting in these siloed realms. And then on the right, what integrated forecasting encompasses. Its methods and processes, just like it has always been, but now it's also considering scenarios and uncertainty. And of course, there's data. It takes new tools that can perform these tasks with these massive data sets and provide meaningful, harmonized forecasts between system levels. Next slide, please. Interesting dynamics at play in the area of DER interconnection for T&D, as bulk system planners are starting to have to pay attention to aggregates of these distributed resources. And distribution planners have to start thinking about the aggregate effects that their DERs are having at the bulk level. System standards and requirements are needed to satisfy both. We're seeing things like flexible interconnection provisions and DERMS to manage local system constraints. and at the same time, things like for 2222 to make way for useful aggregated operation at the bulk level. Next slide, please. All of that leads right into this next slide here. Virtual power plants and distributed energy resource management systems provide real-time control of distributed resources to enable better control of DERs on the distribution side, and with VPPs, integrated dispatch to meet the needs of the bulk power system. Next slide, please. What we're showing here is a roadmap that was created by one of our researchers showing how technologies deployed across a utility system can evolve, beginning with a GIS system as a foundation on the left side, then adding some control and bringing in more data with systems like DMS and AMI, all the way up to eventually implementing systems like Advanced Distribution Management Systems, ADMS, which can enhance the ability to monitor, control, and automate grid operations, leading to faster fault detection, isolation, and restoration, and significantly improving reliability. Along with modernization can come tools to help with some of the challenges that we talked about, especially resilience and DER integration. Next slide, please. Deploying and integrating these new technologies does not come without its own challenges. I'd like to quickly tell you about this project that was a collaboration between NREL, Schneider Electric, ADMS Systems, and Xcel Energy to evaluate ADMS implementation and quantify savings from voltage optimization on a high-demand feeder. The ADMS testbed at NREL, funded by Department of Energy, was used to de-risk ADMS implementation and identify device interoperability. The goal was to reduce power, save energy, and maintain voltage within operating limits, aiming for solutions that avoid additional costs and equipment impact. Next slide, please. Cybersecurity standards are being developed and implemented. Showing a couple example resources here. NARUC cybersecurity baselines, which is not a standard, but provides guidance for regulators, utilities, and DER operators to align on helpful standardized approaches for securing distributed resources connected to the electric distribution grid, and the IEEE 1547.3 standard, which focuses on cybersecurity for the interconnection of DERs. Next slide, please. And so we come to thinking about T&D together. The two big areas that take up most of the energy of these folks are reliability of the parts of the systems they're responsible for, and then planning investments in those systems in increasingly integrated ways. Next slide, please. Once again, the nature of these systems, of these system levels, sometimes calls attention in different directions. Here are some of the things that come to mind with distribution engineers and bulk system engineers when they think of the term reliability. At the distribution level, reliability indices, tracking that 300 minutes of downtime every year, designing operational flexibility into the system with feeder automation and DER integration, and resilience, moving the needle along the continuum to consider not only outages during design conditions, but the evolution of outages and restorations during major events. And to bulk system operators, reliability is adequate resource for expected load and outages, operational reliability to handle contingencies and uncertainty, and extreme weather and other hazards. More and more, these two teams are crossing over into the others' worlds and thinking about things that the others are thinking about. Next slide, please. So we've seen some of the tension in priorities. and focus between system levels, and increasing efforts to harmonize. The goal at the top of the staircase here is co-optimization, ultimately making investment decisions that optimally include the needs and benefits of the entire system. The evolving grid demands a coordinated planning approach that spans generation, transmission, distribution, and even customer resources. Integrated planning efforts are essential to understanding, for example, how DERs can contribute to reducing bulk site expansion needs, and how transmission values influence distribution investments. Getting there begins with awareness, even as simple as distribution and transmission learning to speak the same language, then planning toward the same scenarios and understanding each other's data and processes. Coordinating data is a big hurdle. Sharing that data and standardizing data formats. Moving up the stairs, iterating these processes across G, T, D, and C tools, communicating with each other, and with higher and higher degrees of automation. Integrating planning is a natural development. Integrating more objectives and more topics into planning, and integrating planning activities across system levels is critical in these days. That concludes what I wanted to talk about. So at this point, I'll turn things back over to Jose.
Thank you, Vince. So as we talked with Vince, as we mentioned, one of the hot topics right now is how do you actually bring together transmission and distribution planning? So in this context, there's a bunch of challenges that come from it. And it starts from the fact that these two processes actually happen in different timescales and in different proceedings within the regulation. However, we have to start understanding that the value that distribution with the addition of all of the new resources that Vince talked about can provide to the transmission system are important. So how do we actually move forward towards a coherent system where these two things can happen together is part of the most important considerations when it comes to trying to get the most out of the existing grid assets. Let's go to the next slide. And I'm going to pass it on to Pete to discuss the other aspects about the program.
Thanks, Jose. Yeah, to close things out, as Jose mentioned, this is a complex issue. We know that it has a lot of moving parts to it. There's sometimes information asymmetry between, let's say, the utility and the regulators who are reviewing the planning, proposals, the end results of capital investment plans, et cetera. And so the Department of Energy has seen fit to provide technical assistance to regulators and state policy makers in energy offices on a whole host of different topics, including those that are discussed today. The program can be accessed through the URL listed on the left-hand side, and we offer 3 different types of technical assistance. First and foremost is what we call our help desk. This is where you get up to 4 hours of time of someone like Jose or Vince. Ask some questions, get some answers. Maybe there's a canned presentation they have on the topic you're interested in. It's just a great way to kind of clarify some things that you may not understand, point you to some resources you didn't know existed to really help you in whatever it is you're looking to do. If you need some more exhaustive support, well, then you can move on to our expert match program. There you get up to 100 hours of support. That potentially could allow for more formal review of, let's say, a filed IRP or T&D transmission or distribution system plan, among other things. Maybe even some minor amount of technical analysis. Both of these types of technical assistance can be accessed very easily through our website using about 4 or 5 question intake form. Ultimately, we're looking for 3 or 4 sentences from you on what it is you need help with. Once we receive that, we can then match you up with one of our subject matter experts within the lab complex, and off you go within a week or 2. Last but not least is our deep dive. These are very deep, engaged opportunities, typically taking 9 to 12 to even 18 months to complete. They typically are costing hundreds of thousands of dollars in all cases, the expenses associated with accessing all of the subject matter experts, it's not on you. The Department of Energy is funding this. At this time, unfortunately, the deep dive is not available, but we're hoping with the fiscal year 26 budget coming out, we're hoping that some additional funds will be made available so we can open the window for that. So please, I urge you, do take advantage of this technical assistance program. It is available to anyone in a state energy office or state regulatory office. You can use it as much or as little as you want. So with that, we're going to close things out for today. I really appreciate your time and attention. As I mentioned, there are other webinars in this series. I urge you to either try and register for one of them or just come back to this webpage and you'll be able to access all of the recordings associated with those other webinars. And if you have specific questions about what was covered today, feel free to access Jose or Vince directly at the email addresses listed here. And so with that, I want to thank you again for attending today and wish you all the best.